Good morning, everyone. So, the next topic of study is output stages and power amplifiers. So, this is also known as it's an output buffer, right? For this, the book which I am following is Fundamentals of Microelectronics, as I told you, like it's a second edition which I am following, and chapter number 14 from that. Its name is Output Stages and Power Amplifiers. So, there are for a few terms which has to be understood over here, like generally basic stages which we are going to follow. It might be like emitter follower, push-pull stages and its improved variants. Our study is limited to just a few things, as this is not the the course on power amplifier. So if you like this topic and if you want to further expertise on such things, then you need to study some course called RFIC design, where power amplifier is a separate module, and people generally you have to spend lots of time on understanding of that. The next part might be like it's not only the small signal but large signal which is playing role over here, because we want to have the very large swing. And in that case, when you're doing this, you have to see the omission of PNP transistor is possible or not. Then high fidelity design, all these things has to be taken into account. On top of that, we have to see that the requirement of generally the output buffer or the power amplifiers needs lots of current to be drawn, and having the low impedance at the output. In that case, you have the higher power ratings, and on top of that, it also consumes or you can experience the thermal runaway. And generally, like the most important part of the uh, like any PA classes or the power amplifier classes are depending on its efficiency. And there are certain classes like class A, B and C. I should say class A, class B, class AB, and then like you can have C, D, E, F also. So certain classes are there on the basis of certain things like efficiency and linearity or the non-linearity introduced in your system is actually going to limit the performance, and that's how you give them classes, right? So let's start with the simple thing that the most important thing is till now, like what we have studied in previous chapters, that that was not suited for the high power applications. What I mean to say is that you might have your amplifier, and outside world you are going to connect it to some other instrument, or maybe other thing which will have the input impedance is very low. Let's assume that it's a speaker whose impedance is 8 ohm. Now we are not talking in terms of even 50 ohm. Look, this is much lower than what actually we have studied. Even it's not 50 ohm, it's much lower than that. Sometimes it has to even drive the load of 1 ohm. In that case, it's very difficult to drive from output to this point, as we have studied this. Or if you want to do that, you have to have something in between this circuit, and that circuit we are calling it as voltage follower, if you remember. Also, it might be output buffer or driver circuit, or you can also say that for such a like a low impedance driving thing, you need to burn lots of power through this output buffer. We call it power amplifier. By the way, this has to be like an ideal voltage control voltage source whose input impedance has to be infinity and output impedance has to be as low as 0 or much lower than what you have to uh, drive. So if this is 8 ohm, this has to be like maybe zero point 0.8 ohm or something lesser than that, so that it can drive this one efficiently. Otherwise you may get some loss in terms of voltage. So if you understand that, now we are not talking in terms of something in microwatts of power, but I'm talking about you need to deliver a 1 microwatt of power with 8 ohm of speaker impedance. So in that case, if you want to approximate the peak amplitude, sinusoidal peak amplitude, what you can do, you can use the root mean square RMS value times 1 by RL. That is going to give you the power or the P out. So here Vp by root 2, as I told you, it's a RMS value. Adding this 8 ohm over here and find out Vp is equal to 4 volt. But for given Vp of 4 volt and RL of 8 ohm, you need to find out the how much current is required by my by my speaker. And in that case, you can see that IP is nothing but Vp by RL, and that's almost like 500 milliamps. So it's quite high current, but that is the characteristic, or that is a requirement of your low impedance based speaker. So that is very important over here to understand that now we are not talking in terms of microwatt, and it's a it's a milliamperes of current. So that's why, like, sometimes people are using power MOSFETs also for designing uh, such a thing. Nowadays, even like I have seen that some of the people have migrated to some different technologies. Instead of like CMOS, they are using instead of silicon, they are moving towards gallium nitride or some power MOSFETs, so that they can drive the output, which is actually as low as 1 ohm of resistance. So then that is a very challenging part over here, and we need to design accordingly. So now let's move to the next part, which is important observations. So there are 5 observations are saying that, look, now we are not going to talk in terms of hundreds to thousands of ohms. We are going to talk much lower than that, and that value might be even much lower than 50 ohm. It's not in 50 ohm, 75 ohm, or 100 ohm. It's going to be much lower than that, and it might be uh, depending on the fact that we are going to have the high power requirement as high as 1 watt, 2 watt, or it's in watts. So in that case, you need to make sure that you can able to actually drive the low impedance load. The next part is now the current requirement is not in micro, it's much higher than the typical currents, which is milliamps. So it will be around like 500 milliamps to even it will be in amperes, so it can go in amperes also. So this is just for your information that to what sort of units you need to deal with when you are in power amplifier. And as we are having the voltage swing delivered by the amplifier can hardly viewed as small signal, and we need to understand the whole behavior as a large signal. And on top of that, power drawn from the supply voltage is in the range of 1 watt. It's much higher than what typical values we were talking in terms of micro microwatt or milliwatt. So it's not a low power design, it's going to be, of course, the high power. And but there is no other alternative. You have to have such kind of voltage control voltage source at the output to drive such a low impedance, and that will cost you lots of current, lots of um, current, and you need to see that the resistance is small. And now when we are dealing with such a high power consumption circuit, it's going to hit up, and the the high power transistor must therefore handle high currents and high temperatures. So as I told you, like, there is also some of the technologies like gallium nitride, and some people are also using LDMOS. So LDMOS is lateral diffused metal oxide semiconductor, and gallium nitride is GaN technology with different like you're using different composition, uh, like instead of silicon. So instead of silicon germanium or silicon combination with silicon, we are using some kind of different some people are also using silicon carbide, so to cater such a such a need. Okay, so now let's also understand a few terms like an op amp. When you are designing an op amp, you need to have the good gain, good bandwidth, and like good stability and other things. So here, while talking about the power stage amplifier or the output buffer, you need to make sure that you are dealing with three important aspect of the specifications. One is the distortion. So as we know that distortion should not be there. There should not be the non-linearity. When we are talking about the distortion, it's always in terms of the non-linearity, when the input is not following the output exactly, and there is some discontinuity. So you know about many discontinuous characteristics. Uh, One of them is dead zone, which is going to um, uh, which is going to be seen over here, and that has to be tackled, and that has to be um, taken into consideration to minimize as small as zero. And the next part is the power efficiency. Power efficiency is defined as power delivered to load divided by power drawn from circuit. So that has to be divided, and we need to find out the efficiency in percentage. So it has to be percentage, right? So, and of course, as this is very important to note that voltage rating or the power rating is very useful for a given load. It's not only the voltage which is required, but on top of that, the value of resistance which can be driven by the circuit, it has to be kept manageable, or the output resistance of such a circuit has to be much lower than what is required to be driven at the output side. So such things we need to take it into account. So if we are talking about a circuit which can be a circuit which can act as a voltage follower, we already studied one popular circuit which is a common collector circuit. So similar to what we have studied in common drain. So using MOSFET, if you are interested to deal with, then you can apply the common drain amplifier. Or in the case of BJT, you have to use a common collector. So this is acting as a voltage follower or the emitter follower. This name is also the emitter follower. The best part of this circuit is the input impedance is very high, and output impedance is very low. If you look at this, so this is going to be the common collector or emitter follower, whose input impedance, if you're looking from here, it's much higher, and the output impedance looking from here is much lower. If this is this RL is much bigger than what you have at the at the output. However, if RL is much lower, then output is actually acting as just RL, right? So if RL is very small value, so it has to be taken into account that when you are using such circuit, so the output impedance has to be much lower, so that you can drive the next part of the circuit. So for such a requirement, you can have one circuit which is common collector circuit, where look at this emitter is connected over here, and the collector is connected to plus 5 volt of battery, and other side is minus 5 volt. I'm dealing with plus to minus. However, if you like, you can go till zero also, or having the single supply voltage. However, just to have the dual swing, you can have the plus 5 and minus 5 volt. For like design value of RL of 8 ohm, as I told you, like we need very high current, or you can say that milliamps of current is required. So let's assume that I require the current of 32 milliamps, 32.5 milliamps. That's one number we are using it just to start with an example. So very easily we can find out the gain is nothing but the, if you remember the uh, common drain amplifier, where we used to have the voltage division between two different uh, branches, where one side it's 1 by gm and rest of the side it's output resistance. So uh, as we know that output resistance is like other than 1 by gm, other things are much lower. So you can much lower than 8 ohm of resistance. So anything is coming in shunt with this one is going to be removed, like the impedance of this one is going to be like the current output resistance of current is infinite. Similarly, the base with modulation resistance RO is much higher than 8 ohm. So we can neglect it and just we can keep the voltage division between two resistances, which is 1 by GM and RL. So we can write down the voltage gain as directly RL divided by RL plus 1 by GM. Note that we have assumed that all other quantities are much higher than RL, and that's also the, it's not even you can say that assumption, it's going to be happen because 8 ohm is very small quantity and others values will be in kilo ohms. Now let's assume that zero point 0.8 volt is just a number which is, which you can call it as VBE, because V out is nothing but V in minus VBE1. If this is so when your Q1 transistor, which is BJT, in active mode of operation, V out is equal to V in minus VBE1, or you can say that whatever the input you are giving, it should be having the difference of VBE1, or you can say that it's actually you are clamping your output to VBE1 voltage and you are getting the output. So it's a DC shift either on the positive side or on the negative side. It depends which particular transistor you are using. Similarly, like you can use PMOS like PNP transistor at the bottom side and you can have the clamping at the positive side. But what if like this voltage, I'm not talking till zero, but if it is a dual tail or the dual supply plus 5 and minus 5, it will start with the VBE. So if you look at this, if this is your input, amplitude with respect to time, so if this might be like till 5 and this might be till minus 5, right? So then it will wait for 0.8 volt or the VBE, and then it will track the output. But in this circuit, does it go below this 0 volt or not? The fact over here is it's not a regular circuit where there is a minimum voltage which will be uh, uh, actually which will be developed across RL in the case when V in is 0, but here it will be there. So to understand that, we can look at one example where we know that so this is taken from Behzad Razavi's book. So most of the things has been taken from Behzad Razavi book, but this example is from there, and which says that if in figure 14.1a, which is this one, let's call it 14.1a figure. So in that case, if Is is equal to 5 times 10 raised to minus 15 of ampere, You need to determine the output voltage for Vin equal to 0.5, and one more thing, Vin carries Vin, like what value of Vin does Q1 carry? Only 1% of I1. So this equation is already known to us. V out is equal to Vin minus VB1. On top of that, so this is the circuit. This is IC1. So IC1 is nothing but V out divided by V out divided by RL plus I1. So as per the Kirchhoff's, it has to follow this equation as well. So there are two golden equations which have to use. Since we know that VB1 is nothing but VT ln IC1 divided by IS. So this is derived from this equation, that IC is equal to IS times exponential VB by eta VT, where eta is equal to 1. For eta equal to 1, this has been written over here. So from this, if you combine both the equations, V out is nothing but V in minus of VB1 is over here. So if you do so, we can also like find out one thing when you are saying a few iterations and all, like this has been found out by the simulations by Vezat Razavi's book. However, what I mean to say that if this is 32.5 milliampere of current, so 32.5 milliampere multiplied by 8 is the current requirement, or this is the current which will give you the value of V out when this transistor is off, because this has to be like, this guy is asking for current and that has to be supplied by the resistance. So V out will be depending on such a large value of current multiplied by 8 ohm. So if you multiply both of them, you will get some number like minus 260 millivolt. So you can keep this somewhere when V in is V in is the value for which this is going to happen. So V out is minus 260 millivolt, and just to find out for 260 millivolt what is the value of V in. So value of V in is 0.4 volt, approximately 0.4 volt, for which this V out is 260 millivolt. So as I explain you, like when Q1 is not conducting even after VBE1, but for the given value it will go down, and this value V out is minus 0.26 volt, and this is happening when V in is around 0.4 volt, and thereafter it's stay there and wait for the value which is point like VBE, and then the difference is remain at VBE1. So note that because of this large current, you can experience the voltage going below 0 volt, and that can be seen from this example also. These numbers can be fed over there for a given value of IS. However, it can be find out for different values also if this IS is different. Notably, it has been taken for just for 1%, but I'm saying not even 1%, it's 0%. And then in that case, if Q1 is not carrying any current, then for the complete current taken by this loop, what is the voltage drop, and from that voltage drop, what will be the uh, V in value for the corresponding give you that particular V out, and that's only possible when you have such things. So now let's move to the next part, that yeah, as I have drawn. So here you can see that the output is not exactly tracking what we wanted to have. If there is not such kind of such kind of such kind of things, then it's okay, but this is going to happen, and this is actually known as the crossover distortion. When it's crossing from like positive to negative, you experience that it's stuck to one value at V out, and that is what we don't want. So it's also affecting the linearity. You can see some sort of harmonics in your output, and it's not uh, advisable to have more distortion for having the power amplifier. So if you are using such kind of circuit, like your overall requirement of or overall circuit performances in terms of SNR is very good, and if you're adding this, SNR is degraded, and in that case, if your SNR is degraded or the total harmonic distortion is degraded, your output is going to have uh, worst worst noise performance. So that we don't want. So that's why like this crossover distortion has to be removed. But before that, like just for checking with the number which we have worked it out in the example, we can write down, or we can make these numbers are actually depending on the example which we have given. Notably, this is V1, by the way, for the case, and this V out is nothing but V in minus VBE1, and this number are came from the fact that value of is given to us, and even this one is also from that. So these numbers are actually changing with respect to what current you are feeding, and what value of resistance you have, and what value of the device characteristic you have. So however, these numbers will change, but you can say that the output will go below zero line, and it will follow such kind of characteristic. Or you can say that V in versus V out will look like this one. Now my simple and the best example is, because this one was always giving me output in the positive half with some little bit below 0 volt, but I cannot have the full swing in positive and negative both. So the most important thing is you can use some sort of push pull stage, where you have two transistors, one is NPN and one is PNP. Both are at their end, they are acting as common collector amplifier, and it follows the same similar kind of characteristic what we have for the single transistor. However, we are adding both the transistors together, Q1 and Q2, and they are adding the advantage of both the things. So what exactly happening is, if you have in this characteristic, if you, instead of this, if you have this kind of circuit, this is also common collector, and in this case you can also have minus. So in this case the characteristic will not be like that, but it will look like this one. This is V in versus V out, where this one is actually equal to V in plus mod of VBE. Let's call it VBE1, because base to emitter will be negative over here, but it will be going to give you the negative number over here, right? So such things can be worked out, or you can write down, if you don't like this, you can write down minus also. Yeah. So sorry, V in plus. So if you look at the output, if this is your input, output will follow this one, and the output is clamped to plus VBE1, and yeah. So when you are doing this, you have to again you have to have the problem at the actually positive side, or you can say that the output won't look like this one. Output actually will look like, and this will be your 0 volt line, and of course you need to find out these values as we have found out these two, right? So for a given current and all these things, you can find out those things, but separately, like two amplifiers, NPN and PNP, are having the performance which is not exactly what we want. So what we can do, we can have both the transistors together, and we can see that when Vin is going in positive direction or the positive half cycle, the Q1 conducts and it will supply the current to RL. Whereas if it is negative 1, this Q2 is sinking the current from RL, right? So this is like in one stage Q1 is serving the problem, and in one stage Q2 is serving the problem, or you can say that this is the positive half cycle taken from care by Q1, whereas for Q2 this is negative half cycle taken care by Q2. So my next question might be that sketch the input and output characteristic of the push-pull stage for very positive and very negative inputs. So it's very easy, you can combine both the characteristics just now we found out. So the output might be, or the characteristic look like this one. However, there is some area, like this point might be like VBE1, and this point, sorry, this might be VBE1 and this must be VBE2. So if you look at this in between these two, Q1, neither Q1 nor Q2 are conducting. Right? So they are not conducting. So in that case, the output has to be 0. And this sort of characteristic is known as the dead zone, where there is no output, right? Or it won't go below 0 volt because both the uh, both the negative and positive values are compensated by each other, and the output seen at the output node is actually the 0 volt when this is from VBE2 to VBE1. So drawing the characteristic when this is VBE1 and this is VBE2, you're going to experience the output, but still crossover distortion will remain there. So the amount of crossover distortion might be small, but still it's there because of the dead zone. This is coming because of the dead zone. So let's keep this in our mind that this is a problem from the push-pull stage. And just for the completion, you can see that for the middle range from VBE1 to VBE2, in this the transistor is in cutoff between VBE1 and VBE2, and gradually when we are going this side, Q1 conducts and Q1 will have, Q1 is in active mode and Q2 cutoff, and this one like here Q2 is in active mode and Q1 is in cutoff, and accordingly you can have the gain. So in between these two values there is no gain, so it's a reverse of what happening to the normal amplifier. So if you are taking its push-pull amplifier, then if the top side is PMOS and downside is NMOS, then the characteristic will be different, where in this case the characteristic is reverse, or we need to make sure that if you need to have the good uh, replica of the input with the minus of VBE1, what you need to do, you need to make sure that you should avoiding VBE1 and VB2 area where there is a crossover distortion or the V out is 0 volt. So there is one silver bullet taken from the book. The ear is quite sensitive to the clipping of crossover distortion produced by followers of the push-pull stages. Generally, like with a sinusoidal input at frequency of f in, it's not purely the sinusoidal thing, but it has certain harmonics at 2f in, 3f in, and etc. So if you look at that, our ear is very sensitive to those harmonics. In fact, many enthusiasts, specifically guitarists, the older technology was like a vacuum tube, so from which power amplifiers used to be made. and they prefer that, where it's also known as valves. So it has this softer clipping characteristic than what transistors has. This is for your information. Now if I want to make the improved stage, what I can do, I can add one voltage, like one battery in between the input and the transistor. So what can happen over here? So if this is the case where Q1 and Q2 are NPN and PNP respectively, if I am connecting here, so here I am having V in, but here it's two voltage sources in series, so it will be V in plus VB, and notably V1 minus V2 is equal to VB, right? This is already known to us. Notably, V and V2 are same, by the way. So if this is the case, what I'm saying, if VB is VBE, just VBE, then what is going to happen when your input is 0? So if I'm drawing the input output characteristic, where this is V in and this is V out, when input is 0, this is still in conduction mode, and the output is going to be equal to V in minus VB, right? Because this is the one, right? So this is going to happen here. But what if I'm going below value of 0? So 0, this is not conducting. This is wait for the voltage which is minus VBE, and thereafter it will conduct. So if I choose VB equal to VBE, just VBE, still there is a crossover distortion which will be experienced over there. So what I suggest, let's have VB equal to 2 VBE. If that is the case, the whole characteristic will shift from here to here and pass from this point. Once this V in is minus VBE, then this is VBE, and difference between two is 0, so V out is 0, and where it's crossing this is also VBE. When V in is 0, this is acting as 2 VBE, so output is 2 VBE minus VBE will be VBE, and of course after that this Q2 will take care of the rest of the characteristic. So it's very important to choose this VB as 2 VBE, just to make sure that it will take care of like crossover distortion both sides. So in that case, if this is the case, you can see that, so V out is nothing but V in plus, so this is base to emitter, so it's V out is nothing but V in plus VBE2, right? So you can see that V out is always riding on VBE2 if you look at that, and this VB will take care of the removal, the crossover distortion, right? And the characteristic will look like this one, as we have already discussed. But what if the thing is different? I'm not taking the positive clamping, but I'm talking about the negative clamping. If I'm connecting this V into Q1, and in between Q1 and Q2 and V in, I'm connecting a battery of VB, as we have explained earlier. This is expected to have 2 VB, and both the VBE are depending on, I'm assuming that VBE1 and VBE2 are equal, and those are VBE, and the addition of these two are 2 VBE. So if that is the case, you will have the negative clamping to minus side, and V out is nothing but V in minus VBE1. So you can see that it's always minus VBE1, and you can see that below 0 volt, it's actually, when this is 0, here it's 2 VB, and the difference of these two, So Vout will be equal to minus VBE. So at 0 input it's minus VBE, and at VBE input the output is 0, right? So that's things that are the things we can observe, and we can take into account all these things just to make sure that we are removing the crossover distortion. Now there is no crossover distortion, but the most important part is who is going to give you battery. There is no battery, by the way. You need to use some real components using RLC or transistor or diode. So what we can do, we can add two diodes, but notably I have made the red box over here. Who is going to So generally the diode will work when anode voltage is higher than cathode voltage, and in that case this potential is not defined, or it's not given from anywhere. Or even if you pump the collector current, which is because of Ving the collector current, base voltage the cannot be developed. So this potential will be always at unknown value, or it might not be the value which you want. So what you can do, you need to bias it through some voltage or some current. So what we can do, you can add one current source on top of that, so that the voltage is going to be developed over here, and that will make sense of having two diodes, and always anode is higher than cathode. So in that case this is a PN junction diodes, and when they are on, they are going to give you the equivalent on potential or the on voltage, which is around like 0.7 volt, or it's similar to what we need for the cut-in voltage of base to emitter junction. So that can be taken by the PN junction of this each one of the diode, where each one of the diode has cut-in voltage or the on voltage of VBE1 and VBE2, which are both equal. And so that's what we can do to implement that circuit. One more thing, like we might be interested in current through the source. So here you can see that if this is I1 and this is IB1 and this is IB2 coming from this transistor, in that case the current flowing through ID1 and ID2 will be equal to I1 minus IB1. And of course, for setting the Kirchhoff's current law, the source has to taken care of the current, which is addition of these two, or you can say that I1 minus IB1 plus IB2. This has to be flowing through the voltage source, and that's very important. Just to understand this, I have kept this one. So there might be like, can we use this push-pull stage at the output of op-amp? Yes, actually in most of the op-amps or most of the circuits, we have a power amplifier even in your mobile phone, where you need to drive such a low impedance speaker. And even in 741 we are having such kind of push-pull stage, and integrated op-amps, and many places where you need to drive the outer world, which is not going to be equal to just 50 ohm or much smaller than 50 ohm. Sometimes even driving 50 ohm is also important part. So in that case, if the output is in mega ohms, no, there is no problem. However, if it is very low, you need to add one op amp, sorry, you need to add one output buffer, which is an uh, ideal stage of voltage control voltage. So that can be done by any push pull stage. Okay, so now what I'm saying, rather than doing this at the one side, let's have the two current sources, or one is current sink, one is current source, and you can add both of them. Notably the current flowing through Q3 and Q4 are equal. So this way you are having, this is VBE1 and this is VBE2. So equivalent of VBE1 and VBE2, or rather than making no confusion, we can call it VD1 and VD2, whereas this is VBE1 and this is VBE2, right? So in this configuration also, you are not going to have any crossover distortion, because this is taken care of till till input is 0 and this is below 0 volt. So this will work, there is no problem in that case. And these current sources are, make sure that these diodes are in on condition and the current flowing through both the diodes are equal if Vout is also 0. Or you can say that then this Vin is not going to demand much voltage, right, when Vout is equal to 0. So there is no asking for the current of IC, and there is no IC, so there is no IB. If there are no IB, then the current can flow directly from both the diodes. Okay, but on top of this, I'm adding one more circuit which is similar to this one. I'm not doing this one, but I'm saying that I'm having V in over here and same circuit. Okay, so there are two diodes D1 and D2, and I'm adding this with one additional common emitter amplifier. Look at this. So Q4 is going to give you an advantage. However, I am interested in finding out the current flowing through Q1 in such a configuration. So if you are interested in that, what you can do that if V out is 0, for that what value of V in is required, notably, right? So for that one we need to have value which is VB. So both of them are, let's call it VB. So it's 2 VB already, right? So you need the potential which is VBE. So you need to find out what value of V in which is going to give you V out in this case. So you are giving from downside, right? So that's why like it's a positive clamped, right? So if it is a positive clamped with the VBE, you need to give minus VBE. Sorry, you need to give accordingly the input value from the characteristic given over here. If it is positive clamp, right? Because that is what right now happening. So at V in of, sorry, at when V in is V out is 0, you need to give minus VB, right? So similar thing we can do over here, and you can find out V in. While doing this, you need to make sure that this is 0 when this is also VBE. For having V out to be 0, this has to be VB. Or I can do one thing, I can so if this is the case, I'm saying for V out to be 0, the input of Q1 has to be VBE. And for having VBE at input and each of these diodes are VBE, we can say that to have VBE, this has to be 0 volt. If this 0 volt, then and then the addition of these two is going to give me VBE, right? And we can neglect about other part, and we can neglect about other part, and we can redraw the circuit as follows. So now this is actually a diode circuit. Diode is nothing but, if you remember, you can implement diode using such configuration where base and collector are tied together. When you are doing such things, it's nothing but current flowing through this one, and this one is depending on what ratio of diode and Q1 geometry you are keeping, right? So similar to the current mirror, this is going to happen, and it's depending on what current is flowing through D1 that will be replicated or mirrored on Q1, and depending on actually the D1 and Q1 geometry. If they are exactly identical, there is no problem. Area wise, if they are same, the current flowing through D1 and Q1 are exactly identical. However, if this is not the case, then you will have different value. But we have to make sure that for such a configuration, we are not going to use a direct diode, but we are going to use always this kind of diode connected thing using transistor. So that is what explained over here. If you want to look at the current for that, so ID1 is nothing but, so sorry, VD1 is nothing but VD ln IC3 divided by ISD1. So that's the ratio which is going to play the role over here on the basis of the current of this one. You can find out this equation very easily, or you can derive it, and you can find out IC1 is nothing but the ratio of ICQ1 divided by ISD1, and depending on what IC3 is actually, the how much part of the IC3 has to be flow through Q1 depending on the ratio of these two. So that is what, if both are exactly same, then ISQ1 and ISD1 are same, then IC1 and IC3 will be exactly mirrored. And we might be interested in the small signal gain. So in that case, this is acting as a common emitter, and this is acting as a common collector, or you can say that voltage follower. So first part is nothing but the common emitter gain, which is from V in to Vn to V in, and other thing which is already known to us, it's RL divided by, so RL divided by RL plus 1 by GM1 plus GM2. 1 by GM plus 1 GM2 is depending on because of the fact that there are two transistors, right? Okay, so you can find out very easily from small signal model, and this you can see that minus GM4 is the transconductance of this Q4, and this particular resistance value is the resistance at this node. If you can find out the resistance at this node, while doing this, note that these two are shorted because it's actually the path is short circuit. But if you are doing the frequency response, then you need to add some capacitance also, or like originated because of the D1 and D2. Okay, moving further, you can add the like you can reduce the distortion by feedback. So we know that the most important part in feedback is, so one of the characteristic where it's desensitizes the gain, bandwidth is extended by loop gain, impedances, IO impedances are improved by loop gain, and the distortion, or it gives linearity improvement, right? So we knew all these things. So in that case, if we keep an op amp, so the whole lot which is here can be acting as an op amp, and thereafter we are keeping two resistances in non-inverting amplifier topology. So in that case, what is going to happen if this is increasing? Let's assume that right now plus and minus are not given. So if this is increasing, this is also increasing. If this is increasing, this has to decrease. Look at this, because it's a common emitter, so this has to decrease with the minus minus gain. If this is decreasing, and this is actually has to follow with whatever the number is there, just it's positive clamped by VBE1, sorry, VBE2. And if this is increasing, this is also, sorry, this is decreasing, this is decreasing. So in this loop it's acting as a negative feedback, right? So you can accordingly give plus and minus over here. So my point is, when you are doing this, it will make sure that your distortion is going to be reduced by the loop gain. So each of the harmonics will be reduced by loop gain, and loop gain raised to the harmonic number, right? So that is what we already discussed. We can also we should know one fact, that output is generally sometimes getting zero by some electrostatic discharge or some human voltage. So we are also carrying some voltage, and sometimes we are by mistake connecting V out to zero. So in that case we can add one negative feedback of this transistor, and along with that there is a resistance. So VR has to be, value of this VR across this, it has to be 0.7 volt, right? So for having this 0.7 volt, you need to have this resistance as low as possible, like in some 0.25 or some ohms of resistance, so that if by chance, if this is changing the value, and like in that case this will take care of the whole thing, and it will give you the short circuit protection. So short circuit means when V out is 0. You can also look at the power dissipation. Power dissipation is very easy equation, that 1 by t, that's the time period integrating from 0 to t. So IC times VC dt is going to give you the power, average power. So if you want to have the if you want to have the exact equation, IC is nothing but IC, which is flowing from here, is nothing but I1 plus Vp sin omega t divided by RL. So this is at the output side, and this is, by the way, V out. V out is right now Vp sin omega t divided by RL, and VCE is equal to VC, which is VCC, minus VE, which is already we know it's V out. So Vp sin omega t dt, when you integrate it and all these things, you can find out that the average power is actually I1 times VCC divided by 2. And same analysis you can apply to push pull stage, and you can find out those things are already given in the book. You can actually go through it, and you can, this lecture is only for the motivation for under, to take this particular topic for the higher study maybe. And considering the fact that this is for the BTech understanding, uh, we are not going into too much deep. But if you are interested, there is one course called RFIC Design, Radio Frequency Integrated Circuits, where there is a separate lecture only on, like, separate a big chunk of topic where you are going to talk about the power amplifier. So one more thing, when it's like so much of power is consumed by your IC or your package, then you need to add heatsink on top of that. You must have seen that heatsink is not only used for some like power amplifier and the things, but also it's there in some micros. You must have seen your like if you open the old computers, you must have seen the processor in between, and on top of that there is one heat sink is there. Even for FPGA boards, you must have seen such kind of aluminum things kept on top of your IC package, so that it can sink the heat. So, and this is happening because of such kind of setup. And sometimes, like, people are also adding the fan on top of that, so that it's not going to handle such a high heat dissipated by the operation. So this is very important to have the heat sink on top of that, because this consumes lots of current and power. So it's actually the heating. So like we are almost near to like at the end of the lecture, where we have to look at the different practical measures. One of them is thermal runaway. So as we know that that heating is creating a problem, and because of that sometimes it can damage the whole IC or damage the whole circuit. So in that case, this phenomena is considered as thermal runaway. And one more thing is how much efficiency you are achieving in your circuit, which is P out divided by P out plus the P out plus total circuit. So and on the basis of efficiency in the percentage, people are defining the different classes like class A, class B, and class AB, where like the in class A is the one, it's a low efficiency with high linearity, but another one is efficiency is 78.5% with high distortion also. So distortion was wise, it's very bad. So in class AB, which is actually a trade-off between both of them, and each transistor remains on for greater than half a cycle and compromise between efficiency and linearity. So these are the like standard things, but on top of that there are class C, class D, E, and F are also there, and you can study that maybe in further, like if you are interested in such kind of thing. But even people are doing their final year project on only designing of the power amplifier, and it's not so much simple, because as we are going up, you can understand the requirement of all such things simultaneously is tackling is very difficult. And for that, like different classes of amplifiers needs to be understood, and those are classified on the basis of the efficiency. As I told, like class B is having the efficiency of 78.5%, and other like class A might be 33%, and other will have different kind of efficiencies. So those classes are defined, and on the basis of that you can design whatever the class of power amplifier is required, you can design. So here you can see this is class A amplifier, where there is no problem. Look at this, there is high linearity, right? Class B, linearity is a problem, so it's similar to what we have studied for just the first part. And class C, it's little bit shifted up. So this is what happening. And these are just a conclusive remarks, but this is the starting of power amplifier. You can use this knowledge to develop further, and you can make better power amplifiers. So thank you very much for today. Maybe we can study further things in next lecture.